So for the next one, I have this implicitly defined function. So I have this curve that is defined by, it looks like I've got my x's and y's all mixed up in there. So when I take the derivative of this, I'm going to have to take the derivative implicitly with respect to x. So what that means is that every time I see a y, I'm going to think about that y as a function of x, which means that when I take the derivative of anything involving a y, I'm going to need to use the chain rule. Okay, so let's take the derivative of both sides. So the derivative of natural log of 3x to the fourth will be 1 over 3x to the fourth times the derivative of that, which will be 12x cubed. And that's equal to, so I'll have e to the sine y times the derivative of sine y, which will be cosine y, times the derivative of y, which will be dy dx. Plus the derivative of y is just dy dx. Okay, and now I want to solve for dy dx in terms of x and y. So one thing I might do is start by trying to simplify this stuff on the left-hand side, so I can see that that simplifies to 4 over x. And then on the right-hand side, I can factor out the dy dx. And then to finish solving, I'll just divide by the thing that's multiplied by dy dx. So I'll get dy dx is equal to 4 over x times e to the sine y cosine y plus 1. Okay, the next one. So I have a firefighter Everett raises the ladder of a fire truck to the 3rd floor of a burning building. As the ladder elevates, the measure of angle theta that the ladder makes with the horizontal changes at a rate of pi over 20 radians per second. At what rate does the slope of the ladder change when theta equals pi over 6? So what I want to do is I want to have some relationship between this angle theta and the slope. So I know that the slope of the ladder is going to equal this rise over run. Right? We know that slope is equal to that. Well, what is this rise over run? I know that that's defined to be the tangent of theta. So I can say that slope is equal to tangent of theta. So ds dt is equal to, I can take the derivative of tangent and I get secant squared theta. And then the derivative of the inside theta is just d theta dt. And so I want to find the value of that when theta equals pi over 6. So that will be secant squared of pi over 6 times d theta dt, which is pi over 20. Now, if you want to get a decimal approximation for that, you'll have to plug that into your calculator and make sure you're in radian mode. And the way that you would plug that in is recall that secant squared is 1 over cosine. So if you were plugging that into your calculator, you would want to do you would want to do 1 over cosine. So you open your parentheses, you do 1 over cosine of pi over 6, again in radian mode, squared, and then times pi over 20. So that's how you would plug that in if you wanted to find that value. And it's just going to give you 4 over 3 times pi over 20. So it's 4 pi over 60. And that is the derivative of the slope with respect to, so we don't really have units for the slope here, so we're just going to let that be what it is. So let's start by reading this problem and trying to decide what it's asking. So it says a boat leaves a dock at noon and travels due north at a speed of 5 kilometers per hour. Another boat is heading due east at 10 kilometers per hour and reaches the same dock at 2 p.m. The question is, at what time were the two boats closest to each other? So what is it wanting us to do here? Well, it's wanting us to find when the two boats are closest, right? So it's wanting us to find the minimum distance that between the two boats, and have that minimum be We want to find the time at which that minimum occurs. So let's set up a picture and think about what's happening. So here we have the dock. And at noon, this boat is leaving the dock. So let's let t equal 0 be at noon. So what is this distance? The distance that this boat is traveling is going to be 5t. So, you know, at 1 o'clock, it will be 5 kilometers away. At 2 o'clock, it'll be 10 kilometers away, and so on. Okay. This other boat is reaching the dock at 2 p.m., right? So where is that boat at noon? Well, I know that that boat is traveling east at 10 kilometers per hour. So if it reaches the dock at noon, at 2 o'clock, then that means at noon it was 2 hours out, which would be 20 kilometers. So that's going to be 20 minus 10t, because every t minutes it's getting 10 kilometers closer to the dock. So that is that one. And I want to find when this distance here, d, is the smallest. So I want to find when d has a minimum. So what I need is a function that gives me the value of d. So I know that d squared is going to equal 20 minus 10t squared plus 5t squared. And so if I take the derivative of that implicitly with respect to t, let's see here. So maybe I'll go ahead and square root that. So d equals the square root of all of that. Well, which's easier? I don't know if it's easier to write it with the square root or not. Let's do it without the square root. So if I do it without the square root, then I'll have 2d dt equals, then I'll have, on the derivative of this, so I'll have 2 times 20 minus 10t to the first times the derivative of the inside, which is negative 10. Plus 2 times the 5t to the first times the derivative, which is 5. So then I get that d dt is equal to, well, I can divide all of that by 2d. So let's see, I'll get negative 20 times 20 minus 10t plus 10 times 5t over 2d, and I know what d is. But what I really want is I want when this is equal to 0. So if that's equal to 0, that just means the top is 0. Okay, so that's going to give me what I want. So if I set that equal to 0, and I can multiply things in, so I'll get negative 400 plus 200t plus 50t. So I'll get 400 equals 250t, and then I can divide that over, and I get t equals whatever that is. So 400 divided by 250, 1.6. So 1.6 hours past noon. Okay, so what does that, so 0.6 of an hour, 0.6 times 60 gives me 36 minutes. So it's going to be at 1:36 p.m. The two boats are the closest.